our today's session. And today's speaker is Kateryna Hlyniana with the talk with the talk about let me see, where is it? Neighbour-Count thinning of point processes. Okay, Kateryna, please.
Good evening to everyone, and thank you for opportunity to present here my work. And today I want to discuss some properties of random transformation of point processes. So actually, the idea to consider transformation of point processes arises when I try to investigate properties of point process that arises in Aratia flow, and to understand the behavior of joint particles, like how they maybe attract each other or repel. So I wanted to maybe construct something from more simple procedure. We know that point process that rise in the Aratia flow has quite difficult structure, even though it has good written formulas for all correlation functions. Let us start maybe, and so I just will recall what is correlation functions, or so-called case product density of a point process. So informally, we can say that if we consider a simple point process, that means that we have no more than one particle in each location. So then we will say that if we consider non-equal points in space, like x1 and so on, xn, then to find a point in small balls that centered at points x1 and so on, xn in small radiuses, will be proportional to k, n here, n correlation functions, or n product densities. So now in today's talk, we will discuss some property of just two-point correlation function. And I want to discuss how we can get some properties of attraction or repelling of points, just considering a two-point correlation function. So let us compare the conditional probability to find a point in neighborhood of x, and if we know some additional information. So like if we know that in neighborhood of another point y, we can observe a point, what will be probability to find a point in another small ball? So it will be proportional, like if we write by definition, will be the fraction of two-point correlation function divided by just 1 point, so that is intensity of point process. And if we compare with just unconditional probability to find a point in neighborhood of point x, this will be just 1 point correlation density, we can say. So if now we compare probability of, we will compare conditional probability and unconditional probability. So from this, we will say that like if we find, if we know that at point y we have a point, then in point x we will also find a point, will be bigger than unconditional probability. This is equivalent to such so-called covariance, 2-point covariance function will be greater than 1. So, and the vice versa, if we know that here we have point, but to find a point at another close to it point is less than unconditional, here will be the another sign. So from this we can get such interpretation that if covariance function is less than 1, this means that all points tends to repel each other, or in literature we can find that this called inhibition of a point in points. If g is greater than 1, this means that if we know that here points, then nearby we can find with bigger probability. This will be like behavior of clustering or attraction. And if just equal to 1, so that is a Poisson case, and this means that just location of points independent some sort of course it's not it will not lead to independence, but structure will be similar to Poisson point. And here in my talk, for simplicity, I will consider the case of stationary and isometric point processes. This means that they are invariant to translation and rotation. So in this case, we can just write one parameter instead of two, which corresponds to distance between points. So it doesn't matter where they're located, we will concentrate on distance between them. So the classical examples that I wanted to show is the example of inhibition in point processes. That is a classical way for modeling fermionic systems where we have repulsion between points. And it was shown that such processes can be modeled with so-called determinantal point processes, where k-point correlation function is written as determinant of some kernel that depends on two variables. So we just have the same structure for all k-point correlation functions. So here, easily in the case of Hermitian function k, we can see that like 2-point correlation function is has this form. So covariance.
Kateryna, maybe I missed something. But what is Hermitian kernel? What do you mean?
This means that just exactly this property, that k of xy times like it. In general, a k can be complex function, complex valued function. And so this means just exactly that k of xy times k yx is equal to absolute value of kxy squared. Just this property. So if k, yes, here I write RD, but yes, in general it's complex valued. Oh, and it's not RD, just R. I'm sorry, R or C.
Yes, exactly. Yeah.
Yes, yes. This is my mistake. So here, in case of real valued k, it just means that we have k symmetrical.
I see. Okay, thank you.
Okay, so and in this case, for any x and y, we have that covariance function is strictly less than 1. Of course, we have assigned strictly less for those x and y's where k is not 0. So sometimes it's good to model behavior when we have dependence on some fixed radius and some sort of independence for far points. So here we can regulate this function k. And one of example of such determinantal point processes, they appears in random matrix theory when we consider eigenvalues of Gaussian unitary ensembles, and such determinantal point processes appears when we consider bulk limits. So that means that that's not close to boundaries, but they concentrate like near 0. And the same k appears in description of free fermions. So here we can find more about this. So their example of such a k function is following. And also interesting, what I wanted to say is that I will be interested in close distance behavior. So, for example, so in this example, we can say that for small in distance behavior, the covariance function goes to zeros r squared. So it's very different from just independent Poisson point process. So here points tends to repel each other with such behavior. Okay, next example of well-known behavior of point processes is so-called permanental point processes, and here so the same. If we have okay, if real valued kernel symmetrical, then we have the same but opposite sign compared to 1. So here points tends to form clusters. And like one of known models is models that appears in describing bosonic systems has a Gaussian kernel, and like of course here for small distance relationship we see how points try to attract each other. Okay, so now come back to what was motivating me is point process that arise in Aratia flow, which is like Galician-Brownian motion that starts from each point of line. I don't give here a definition because we know it's we saw it several times here. And we know that starting from each point of the line at positive moment, from each point of the line at each positive time, we have a locally finite subset, and we can define a point process as usual. And well, we know their endpoint correlation function is defined as Pfaffian of like such with such a kernel. So Pfaffian now is much more complicated to calculate. So analysis of point process in the RTF flow, even though.
I'm sorry.
Mhm.
K is equal to C. Yes.
Oh, yes, right. Thank you. Here is C, this C, yes. Okay. So even though we have a nice formula, okay, we can find explicit formula for 2-point correlation function, but for more bigger K, it's quite challenging now. But today I will concentrate just on 2-point correlation function, and here actually we have this quite nice formula in terms of Gaussian integral. And just having upper bound for this integral, we can get their upper bound for covariance. I'm sorry, for covariance function. So here we will see that we can see that for ratio point process G is less than 1. This that shows us that points are more likely repel each other than attract, and we can see their short range behavior when R is close of such form. And for R, when R tends to infinity, we consider G of R tends to 0, of course, and to 1, and we can find easily the speed of this convergence to 1. And actually we use this property that on long distances we have almost independence to prove central limit theorems for functionals of point of this point process. So here the behavior we can see like this, and like my idea was can we somehow obtain the similar behavior of attraction or repelling of a point processes by more simple transformation. Just when we have, okay, I start from Poisson point process, assume, and I want somehow thin them, so just remove some points in such way to model the repellent. So here we can see the repellent with such rate. So this was my motivation, and to understand what do we need to do is to, okay, let us start from classical known examples of when we delete points from Poisson point process. So we can retain each point independently with some fixed probability. If we do this, it's known that the result will be again Poisson point process. So we actually did nothing if we just delete independently the points. So another known example is so-called Matern first thinning of point processes that keep a point X in a point process if and only if it is isolated. So this means that we fix some radius r, and then if in the ball with center x, but without the point itself has no points, then we will remain it. And for such point process, like it's easy to find the intensity or one-point correlation function. So here it's stationary, so we just can say that intensity measure is this. And here it is. And the correlation function on distance as like it's quite how to say, it has the repelling is very hard, so you cannot find a point in neighborhood of each point of fixed radius r. So for s is smaller than r, we have 0, then g is grows to 1, and after this it is independent. So in such a case, like how we can interpret, I just said that for small distances we have hard repelling, so it is 0. Then for slightly bigger radiuses, like here is written, we have opposite. So we have greater than 1. That means that on the in this ring around the point, you can find another point with higher probability, given a point in the center. And for distances more than 2r, we have just independence location. So here, opposite from determinantal and permanental point processes where covariance function didn't change sign comparing to 1, here it's change sign. So here we see the behavior in close neighborhood is repelling, and then on this ring conditional probability is higher to find a point. Okay, so now my idea was to consider like the transformation which will be not so independent as independent thinning of Poisson point processes, and not so hard as previous. So in previous hard, like we have here, 0, which is not good for our case. So my idea was to consider point the transformation where we keep a point with a probability that depends on a number of neighbors in fixed radius. So here, for now, if we fix r and we choose a function p, which will be the probability of keeping a point in the process, then I will denote by nr the number of neighbors in a point process x in neighborhood r, and then transformation tr will keep the point each point x in point process x with probability of p that depends of number of neighbors. And here, formally, we can define it such procedure by marking original point process with independent identically distributed uniformly on 0, 1 random variables x. So we just see if its ux is less than 0, then we will keep point x. So now the question.
Kateryna, I have a following question. You said that we can formally do this using independent random variables, but if we have 2 points, for example, like this one, this is 1 point, this is another point, and these circles of radius are overlapping, then at least from this definition, they are not, these quantities will not be independent, yes?
Yes,
But you
this
said that you want to have independent.
Yes. So here, I delete these 2 points using this independent weights. So for each point,
This procedure is not the same as this in your formulas for y, yeah? Because it looks like that in formula for y, you just say, okay, let's kill the points which have a lot of neighbors in the ball of radius r, yeah?
yeah.
But then you said, okay, let's forget about neighbors, counties of neighbors. Let us mark every point of our initial point process by uniformly distributed independent random, independent, yeah? Then it occurs that if you will put here this u of x instead of this, okay, you use it here.
Yes, yes.
Okay, I see. So you just say, okay. Thank you. Thank you.
Yes, it's
Yeah.
okay to understand. I guess so. Here, I just show that, like as you say, we have 2 points xy, and yes, we count even like if their neighborhoods, neighborhoods intersected. But yes, like p is dependent, like for each x and y, they're dependent on local configuration of nearby point x. But then knowing this local configuration, we will kill this or not kill independently with this probability. So we killing them independently, but probability, this probability depends. Like this probability depends on configuration nearby.
Okay.
Okay, so now the question is about like I wanted to see how 2-point covariance function will depend will change depending on rule p and on radius r when we change. So I start from intensity, density, and actually if we start from, like, for simplicity here, I will consider in homogeneous point process with constant intensity, then intensity of transformed point process will be like, okay, this of this form. So here we just use for just we need to find expectation of such sum, and because ux independent, and we can just this we can calculate the expectation of we know that number of points in neighborhood of each point x in Poisson point processes has Poisson distribution. That's that's why we have here Poisson distribution of this form. So here actually expectation of P from Poissonian random variables with this intensity. And for further to find the formula for two-point correlation function, I introduce such notation. So this is just volume of intersections of two balls. So here just unit vector. So we can just say that this is intersection of two balls on distance t in RD. So because on next step we need to know how much this probability of Pn will intersect. And well, if I start from homogeneous Poisson point process with intensity lambda, then then I can consider their correlation function. So here transform point process will be also homogeneous and rotation invariant. So we just consider pair correlation covariance function that depends just on distance between points. And we have here this formula. So here actually the expectation of product of P is our rule probability, which says us with what probability to leave point. And here U and V1, V2 are Poisson point processes, and like this U here is show dependence. I will not write the precise proof of this formula, but on picture we can see why this appears. Like, of course, we know that on non-intersecting subsets, Poisson point processes has independent the values of point which are independent and has Poisson distribution. So we just need to consider two cases, like here in this formula on previous slide. Here indicator appears, which just need to be added if distance between points less or equals than r. So this just representing on this system that on this picture, that if we have 2 points that are on distance less than r, then okay, we have this intersection, which of this random variable u there, which is common, and well, we retain each point here, like we keep point x with probability that depends on points in this area. So this will be u plus independent v1, and the same for y. This will be number of u plus b2. This will be the same, they have equal distribution. And just in case when they're on distance more than r, we do not need to add this point, like +1, just because of this picture. So if points on the distance more than r, we have just like our probability to keep the point depends on this independent values of v plus v1 for point x, and the same u plus v2 for the point y. So here once more on this formula, this is exactly u, the Poisson point process that corresponds for intersection, like this omega d is volume of intersection, and v1, v2 volume of remaining parts. Okay, so this formula can be obtained, and now the most interesting what we can get, what kind of behavior we can get depending on different rules P. So here let us assume that P from 0 and 1 is greater than 0. This means that with non-negative, with positive probabilities, we keep points if they have no neighbors at all, and we keep if they have at least 1 point. So with positive probabilities, we will keep them. Okay, so here I denote, so my distance will be proportional to radius r of the radius of interaction ball. So if the distance from r to 2r, so here the multiplication constants t from 1 to 2. So this means that we are on this. So here point x. So we consider how points like on these distances, or what we can observe here if we know that point x here. So, and we see that for small r, this will be positive. So I'm sorry, this will be like, of course, up to this term. Mu, I'm sorry, I didn't write, maybe it's good, right? So here is like rd from this formula. So this r to power d here, second power r to power 2d. So for this distance, we will have some all the time. We will have that pair covariance function is greater than 1. Like, of course, unless this is 1, so this term will disappear. But in such case, if it's not 1, then it remains, and we have strictly clustering property on this ring here. But for small radius dependence, like inside the ball radius r, so here we see that for inside ball, everything like we can have as positive, I'm sorry, as attraction and as repulsion or Gaussian or inhibition, I'm sorry, attraction or inhibition, depending on what is this. Is this greater than 1 or less than 1? And on this term, like this term will add something else. So for this case, we will have I'm sorry, I need to delete it. Okay. And here also, please note that I here considered in previous case, I considered the case when P of 0 is non-negative. And you can see here that when we divide by 0, like it should tends to infinity. So when P is 0, this formula doesn't work. But from the definition, actually, we can find their formulas for this case. So they are actually show how fast it goes to infinity for small radiuses. And here, actually, this is not something that maybe it's not of interest, because when r tends to 0 and you just say that, okay, I will consider the if I need to kill this point, so P of 0 is equal to 0, this means that with probability 0 I will keep this point. So actually I will delete it for small r with high probability, like in this case. So I will delete it like for small r, we will delete almost everything. So this just means that in this formula for G, when we divide a 2-point correlation function of intensity function, so here actually intensity function tends to 0 too fast. So that's why it's like blows when r is small. So maybe this case is not of interest, because we just actually kill almost everything for small r. Well, when r is small. Okay, so now I wanted to consider some examples to show exact behavior for given functions p. So if we consider p of n of such form, where I recall that we keep the point with this probability. So if we have n neighbors, then we keep them. And as we saw in formulas for covariance function, the answer depends on fraction, how that depends this probability. Actually, now in this case, they are constants, and here we will see exactly what I tried to describe. Like in this case, when on distance of r from r to r, so here we have this sign, that means that we here we with bigger probability we will find the point, we observe point x here, but inside the ball we will have repulsion. So here we will find point with lower probability. So this is what we wanted to construct, but here we have, okay, yes, this is how we have repulsion that we wanted to construct, that this is less than 1 just because of this s square, which is proportion to of p of 2 neighbors to p of 1 neighbor of killing. Okay, so another example is which will like that one where we were talking about that we kill almost everything. This is but we will have more clusters. So here, if we kill carefully, then of course, like here p of n of such form. So if n is equal to 0, we have just 0. And here, everything like this, everywhere, covariance function is just greater than 1 for small radiuses. And I try to I did a simulation for like how this cases looks like, and this is initial Poisson point process. On the next and right here, we just kill p of 0 is equal to 1. So this means that we kill points if they have no neighbors or everything else is 0. So we keep points if they are lonely. So here just we see that this is like here you will not find a point on distance r. And the next example, what I showed in my calculation, here you can find that some points keep close to one to another, but not so often as in initial Poisson process. So like even though in Poisson point process everything is independent, but simulation shows that actually you can find pairs of close points, pairs or triples of close points with like quite often. And the last picture shows clustering. Actually here, compared to previous points, to previous picture, yes, we can see like a lot of empty spaces and some clustering of points. So this was an attempt to give interpretation of neighbor-dependent thinning of point process in terms of two-point correlation function, like how we can give interpretation in terms like if points repel or attract each other. And since I have a little bit more time, I also want to show how we can measure a distance between distributions. So we, for example, here we kill some points, and well, now we want to ask how far they are from, like if we will have a Poisson point process with the same intensity function, like is it far or close of their independent location of points. So in this term, we consider, I just present one theorem that obtained quite easily by using construction of my transformation of point process. So here I consider, I'm sorry, I didn't write the notation, so I will just explain. So we have L, that will be law of point process in the space of point measures. So law of transformed point process, and here, I'm sorry, law of Poisson point process. So here will be like P independent is just independent thinning of X that retains each point with probability MP, which is just the intensity of transformed point process. So if we start from this Poisson point process, then after transformation, after killing some points, we will have this intensity of point process. So the distance of the in total variation between two distribution on a bounded region W, like I estimated. So I assume that W is fixed, so this will be a constant. And here we will have just expected values of absolute values. So here we will have just, I'm sorry, like L1, like centered P of Poisson random variable with this intensity measure mu. So this just this random variable, and this is its mean value. So this is just absolute value of deviation of random variable P of Poisson minus its mean value. And so here their proof is quite simple because of our definition of transformation. So if I will use such a coupling characterization of total variation distance that is infimum of probability that two random variables, in my case it's two random 2-point processes is not equal, where this is couplings. And because we think the same, so here Poisson point process we obtain from the same x, and we just delete it with fixed probabilities. We guess fixed probabilities m small p. Here probabilities depends on number of neighbors in neighborhood. So just because we get them from the same, we think the same point process, then point processes are not equal if we have some, if this some of these indicators are not equal, and just finding this probability that we kill point X in one procedure but didn't kill in another procedure. This is exactly this. If we know, if we have given point process X, then this is the conditional expectation to, conditional expectation to have to kill in one case and do not kill in another case, in another procedure. So this gives just their upper bound in the theorem here. So for now, this is all what I wanted to say. And once more, just maybe I will stop on this pictures. Yes, how we can analyze their how random transformation can lead to clustering or to repelling of points if we start from Poisson point process where points are just independent. Okay, thank you for your attention.
Thank you very much. Maybe somebody have questions or comments, please. Kateryna, I remember that there are a lot of very similar transformations when we have point processes on the lattice structure. Like we can put points only in the on the lattice. Yes?
Right.
And then people are interested. Yes, exactly. And then people are interested in the iterations of such similar procedure. So what happens in your case if you apply the same procedure again?
So this is like what I wanted to do the next. Yes, I wanted to do interaction to yes, interaction of this and to see what will happen. But like this was just the first step to find, because here everything is simple when we start from Poisson point process. When we now will apply the same transformation, but to not Poisson point process like now, like even two iteration. Now their argument is has some dependencies, and even write precise formula for 2-point correlation function now is not so easy. So there.
It looks like you do not need. It looks like you don't need the precise form of the correlation function, because you get some asymptotics, and you need the same asymptotics after iteration. So it looks like you can calculate, and it will be very useful to look at the lattice situation. For example, you can find a lot of literature and even a lot of good simulation for so-called game life. It is called life when we kill points on the lattice depending on the number of the neighbors.
Right.
And it is interesting to look even for destiny of the finite populations, yeah. But in infinite case, we can think about clusters. And another question is following. There are a lot of definitions of what we are calling cluster, and maybe you can input these definitions just looking for clusters. For example, relatively to Euclidean distance, firstly, or to some kernel. In the first picture, when you have Poissonian point process, and then look what will be real clusters in the after your transformations. Yeah.
Right.
And it will be interesting question: what is the diameter of regular clusters? What is expectation of the diameter, and so on? Yeah.
Yes. It will be interesting. Thank you.
Okay. Thank you. And if there are no other questions, then for today that's all. And as far as I remember, next speaker will be Kateryna Kostaryova. Am I right?
Yes.
Okay, good. Okay, then for today that's all. Thanks everybody, and bye.
Thank you.
Okay, bye. Bye.
Thank you. Bye.